In the coming lectures, we are going to talk about the so-called subset sum problem. So first of all, what is the problem itself? It is one of the most crucial problems in complexity theory. So the problem is that given an A set of integers a1, a2 up to an, and the question, is there a non-empty subset of that A array such that the sum of the subset is a given m integer? So for example, we have a given array with values 5, 2, 1 and 3. Of course, this problem is dealing with integers. Okay, and the total sum is equals to 9. So what does it mean? That we are looking for a combination of the items that sums up to 9. If we sum up these values 5 plus 1 plus 3, then the result is 9. This problem is dealing with Boolean values. We are going to return yes or true Boolean value if we are able to solve the given problem. So if we are able to find a combination of the underlying integers such that the sum is equals to a given value. This is an NP complete problem, by the way, and it is a special case of the knapsack problem. So for example, we have a one-dimensional array of integers 4, -2, 2, 3 and 1, and the aim is to find a subset of this array such that the sum of the values is equals to 5. Of course, there are several solutions. For example, if we sum up 2 and 3, of course the result is 5. We can sum up 4 and 1, as you can see, or we can sum up 4, -2 and 3. So there are several solutions to the same problem as far as the subset sum problem is concerned. So I guess you get the problem itself, that we have a one-dimensional array of integers and we want to select a subset of these integers such that the sum is equals to a given predefined value. Okay, so the naive approach or the brute force search generates all the possible subsets of the original array, and because there are 2 to the power of n possible states, the running time complexity is exponential. Then of course the brute force approach has to consider these subsets on a one-by-one basis, so basically it has to do a linear search in ortho and linear running time complexity and has to check whether the sum of the items is m or not. The dynamic programming approach has pseudo-polynomial running time again, as we have seen with the knapsack problem. So it is maybe misleading because we may come to the conclusion that it has a polynomial running time complexity, but in fact it has an exponential running time complexity as far as the size of the input is concerned. So we are going to talk about pseudo-polynomial running time whether in this course or I have another free course on complexity theory and you can find free lectures on these topics. Okay, so you may pose the question that what about the subproblems? Whenever we are dealing with dynamic programming, we are looking for overlapping subproblems and the so-called optimal substructure, which means that we can find the optimal solution for the original problem by combining the optimal solution for the subproblems. So in this case, what is the basic idea behind subset sum problem? What's crucial that again, for every single item, we can make a decision whether it is part of the subset or not, which means that we can include the given A sub I item or exclude the given A sub I item from the subset. So this is why if we want to solve this problem with recursion, then we have a solve function with 3 parameters. A is the underlying array or the data structure containing all the items 4, -2, 2, 3 and 1. We have m, that is the sum basically. So here, for example, the m is equals to 5. So we are looking for subsets that sum is equals to 5. So the capital M is the sum and I is going to represent the first I items we are going to use. So let's consider the last item. We have 2 options. We may include that given item in the subset. So let's consider the last AM item with value 1. We can include that item in the final solution or exclude that value. The problem is that we don't know in advance. If we include the last item an, then what do we have to do? We have to call the solve function recursively Of course, the underlying array data structure is not going to change. The capital M is going to change because we have already included 1. So for example here, if M is equals to 9 and we have the values 5, 2, 1 and 3, if we have already considered for example 3 and we are looking for 9 as the sum, of course we have to decrement M by 3 because in the next iteration we are going to solve the subproblem. So we are looking for 6 as the sum with items 5, 2 and 1. So this is why we are going to call the function recursively, and if 1 is part of the subset, then we have to decrement the value of capital M by the value of the given item, in this case 1, and of course we have to consider I minus 1 items. So I is going to represent the first I items we are going to use. If we use the last one, then we have I minus 1 items to find the right solution. Okay, so this is what's going to happen if we include the last item in the given subset. And of course we can decide that we are not going to include that given item in the given subset. So in this case we are going to call the function recursively. The array data structure is not going to change. Of course M is not going to change because we have excluded the actual item. So we are going to use the previous I minus 1 items, so all the previous items, in order to find capital M, so the sum. Of course, for example, if we take the example we have been considering, where we have items 5, 2, 1 and 3 and M is equals to 9, if we come to the conclusion that the 3 is not going to be part of the subset, then we have to consider 5, 2 and 10, and we have to pose the question that is it possible to sum up these values in order to get 9? So as you can see, in this case the M is not going to change because we have excluded 3. Okay, so basically if we exclude the given item, then we use the exact same approach for the previous I minus 1 items. Okay, so this is why we can construct a formula like this. In the next lecture we are going to take a look at a concrete example and it is going to be clear. I just want to show you the mathematical meaning of this formula. So we are going to use a dynamic programming table as usual. It is a two-dimensional table with row index I, column index j. So again, a good question is that what is this dynamic programming table? This dynamic programming table is going to show us the subset of the first I integers that sums up to j. If j is equals to 0, then of course the value is true because we can always make the empty subset to end up with sum 0. Of course, if we do not have items to sum up, if the I is equals to 0, then of course we return false because we are not able to achieve j if we have no items. So this is why if I is equals to 0, then the value is false. And otherwise, what do we have to do? Of course, if j can be constructed with I minus 1 integers, so if s I minus 1 and j is true, so what does it mean? That we can calculate the sum of j with I minus 1 values. Basically, this is the case when we exclude the ith item. Okay, so let's consider the given example. We have the one-dimensional array with values 1, 2 and 3, and the sum is equal to 5. Is it possible to combine the integers in order to get 5? Of course, 2 plus 3 is equals to 5. Then of course, if it is possible, so if we can solve this problem with 3 items, then what if we have an additional value 4? Of course, we have already solved the problem with 3 items, now we have an additional item 4, so of course there is a solution for the problem, we just have to combine 2 and 3 again. So this is why if we can solve the problem with I minus 1 items, of course we can solve the problem with I items or I integers. So this is why if s I minus 1 j is true, which means that we are able to combine the first I minus 1 items that sum up to j, then we can do it with the help of I integers as well. So we are going to copy the value as you can see. And otherwise, what do we have to do? Basically, this is when we include the ith item. So we come to the conclusion that we are not able to use the previous I-1 items or I-1 integers that sum up to j, so we try solving the problem by including the item I. So this is when we include the ith item, and this is why we have to decrement the value of j. What is j? J is equals to the sum. So if we include the item I, then of course we have to decrement the j by the value of the item we have included. This is exactly what we have been talking about here, by the way, that if we include a given item, then we call the same function recursively, but in this case the sum must be decremented by the actual value because we have included that given item. So we have the one-dimensional array of integers 5, 2, 1 and 3, and m is equals to 9. What does it mean? That we would like to find a combination or a subset of the array that sum up to 9. So for example, 5 plus 1 plus 3 is equals to 9. So we can form a subarray based on the original array that if we sum up the values in the subset, we end up with capital M, which is 9 in this case. So we are going to combine subproblems again. The number of columns is equals to m plus 1 because we start with 0, 1, 2, 3, 4, 5 up to 9. So what does it mean? It is going to be the j index, by the way, as far as the mathematical formula is concerned. So j is the second index as far as the dynamic programming table is concerned. And what does it mean exactly? The first column is going to represent the subproblem if m is equals to 0. Then the next column is going to represent the subproblem when m is equals to 1. Then 2, 3, 4, 5 up to 9. So what does it mean? That for example, as far as the fourth column is concerned with value 3, m is equals to 3, it means that we would like to create a subset out of the original array such that if we sum up the items, the result is 3. So for example, 1 plus 2 is equals to 3. So this is a subproblem. So this is the basic idea behind dynamic programming, that we are dealing with subproblems because subproblems are quite easy to solve, and then we combine these subproblems in order to get the solution for the original problem. So every single cell in this two-dimensional table is a result for a given subproblem. What about the rows? The rows has something to do with the integers 5, 2, 1 and 3. As far as the first row is concerned with index 0, in this case we can use 0 integers. What about the next row? In this case we can use the 5 integer in order to get the value of the sum. Then in the next row we can use the first two items 5 and 2, then the first three items 5, 2 and 1, and finally all the items 5, 2, 1 and 3. So we can combine these values in order to get the given sums. Okay, so of course the first row is going to contain false values because if we don't have items, then of course we are not able to compute the j values as far as the actual sum values are concerned. What about the first column? The first column is going to have true values. Why? Because if j is equals to 0, it means that we have to combine the items in order to get 0. Basically, an empty item will sum up to 0. This is the trivial solution. So this is why the first column has true values. Okay, let's see the second row as far as index 1 is concerned. In this case, we can use the first integer with value 5 exclusively. Is it possible to get the value 1 if we have a single integer with value 5? Of course not. Is it possible to get the value 2 if we have a single integer 5? Of course not, until we get to number 5. Is it possible to end up with m is equals to 5 when we have a single item with value 5? Of course. Is it possible to get 6? Of course not. 7? Of course not. 8 and 9 are also false. So we are going to return true, of course, if it is possible to compute the actual value of m with the help of the underlying integers. What about the next row? As far as the third row is concerned, we can use two values, the first two integers 5 and 2. Is it possible to compute the item 1? Of course not. And by the way, we can use the dynamic dynamic programming table with the formula we have discussed in the previous lecture. Basically, what do we have to do? We have to check the Boolean value in the previous row, and if that value is true, then the value is going to be true in the row below, and otherwise we have to use this formula. So in this case, we have to calculate 1 minus 2. 1 is j, so the column index, and I is equals to 2, so j minus 1. Of course, in this case, because we end up with a negative value, we copy the value above. Okay, in this case, we have to use the formula. So as you can see, we have to use the dynamic programming table with row index 1, column index 0, and it has the value true. And of course, if we consider that we have two integers, 5 and 2, and the value we are after is 2, of course, is it possible? Because if we have a subset with the single value 2, then the sum is 2, of course. What about 3? It is not able to combine these values in order to get 3. Again, it is impossible to get 4, but of course it is possible to get 5, because we just have to use the subset with a single item with value 5. Then is it possible to get 6? Of course not. Is it possible to get 7? Of course. If we have a subset like this, 5 and 2, and we sum up the values, then we get 7. We are not able to get 8, and we are not able to get 9. What about the next row? In this case, we can use the first 3 items, 5, 2, and 1. Is it possible to get 1? Of course, because we just have to use a subset with a single item 1. Is it possible to get 2? Of course, we have to use the value 2. Is it possible to get 3? Of course, we have to combine 2 and 1. Is it possible to get 4? It is not possible. Is it possible to get 5? Of course. 6, of course. Then we get 7. Then we get 8. And we are not able to get 9. Then what about the last row? In this case, we can use all the integers 5, 2, 1, and 3. So this is how we keep combining more and more complex subproblems in order to get the final result. So in this case, we can use all the integers. So basically, all the values are going to be true. So we can get 1, 2, 3, 4, 5, 6, 7, 8, and 9 values if we can form a subset based on all the integers. And of course, the result is going to be the item in the last row and last column. So it is a true. What does it mean? That we are able to solve this problem. We are able to combine this one-dimensional array with values 5, 2, 1, and 3 in order to get value 9. But a good question is, what integers to combine exactly? So what do we have to do? Again, we have to compare the items right above and right below each other. And if the values are not the same, it means that we have to include that given item. So in this case, false is not equals to true, which means that the last item, so integer 3, is in the result set. So we have to include 3. Then what do we have to do? Because we have the integer value 3, and actually we are with integer value 9, 9 minus 3, so the column index minus the actual value is equals to 6. And of course, we have to take one step upwards because we are not able to consider the same integer multiple times. Okay, so we have to compare the two items. False is not equals to true, which means that 1 is in the result list again. And we have to subtract 1, so this is why 6 minus 1 is equals to 5. So we have to consider these items. Of course, true is equals to true, which means that 2 is not in the result list, so we have to keep going upwards. And true is not equals to false, which means that 5 is in the result list. Okay, and of course we have to decrement the value by 5. 5 minus 5 is equals to 0, so if we hit the column index 0 or row index 0, then it means that the algorithm is over. So the result of the subset sum problem is that we are able to combine these integers in order to get value 9, and we have to use the last item 3, then we have to use 1, and we have to use 5. And of course, because 5 plus 1 plus 3 is equals to 9. So this is how we can solve the subset sum problem in pseudo-polynomial running time complexity. So first of all, let's create a class for the subset sum problem. And of course in the constructor, so in the initialization block, we are going to get the integers, so the nums, and we are going to get the sum, so m basically. Okay, so self.nums is equal to the nums, these are the integers, and of course we are after the sum of the subset, so the capital M in the theoretical section, it is going to be the m. And of course we have to define the dynamic programming table. We are going to initialize the values to be false by default, so 4 in range, and we are going to have as many columns as the value of m plus 1, and of course we are going to have as many rows as the length of the num, so basically the number of integers plus 1. So this is what we have been talking about, that if m is equals to 9, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 columns, so m plus 1. If we have 4 integers, then we have 1, 2, 3, 4, 5 rows, so the length of the list plus 1. Okay, so this is exactly what's happening here, and then we have a solve function. Of course, first of all, we have to initialize the first row and first column. The first row has false values and the first column has true values. Of course, the initial value is false, so we just have to bother with the first column. So what do we have to do? We have to iterate through for I in range length of the nums plus 1. Self dynamic programming table as far as I is concerned for the row index, and the column index is equals to 0 and it is equals to true. Okay, and then we have to construct the table with the cells one by one. Okay, so we have to iterate through the row index in range 1 because the first row and the first column has something to do with the base cases. So this is why we are going to start with the second column and the second row with indices 1. And of course we have to iterate through the number of items in the list data structure plus 1. Then we have to do the same for the column index in range 1 up to self.m plus 1. First of all, what's extremely crucial that we would like to avoid index out of bound exception. So here in the formula, we have to use j minus I, so the column index minus the row index. So if the column index is smaller than the row index, we are going to copy the values from the cell above. Okay, so if the column index is smaller than the actual item in the list data structure, sorry for that, so the column index is not smaller than the row index. I mean that the column index is smaller than the actual value, the actual integer, as far as the given row index and minus 1 is concerned, because indices starts with 0. It is absolutely crucial because here, if we take a closer look at the formula, j minus the list data structure with index a minus 1. And of course, if j is smaller than I minus 1, it means that this index is going to be smaller than 0. That's going to yield an index out of bound exception. So this is why if the column index is smaller than that value, then we are going to copy the value from above. So I and j is equals to the dynamic programming table with index I minus 1 and j as the column index. Oh, sorry for that. Here we have row index and column index. Okay, so we have row index and j as the column index. Okay, and else we know that the j is not smaller than the given integer value in the list data structure with index row index minus 1. So what do we have to do? Basically, we have to use the formula we have been talking about in a theoretical section. If the S, so the dynamic programming table I minus 1 and j, so if the item above has a value true, then we are going to exclude the actual I item, and otherwise we are going to include the item in the subarray. So we just have to check that if the row minus 1 and the column index, so if the cell above is true, so as you can see, the dynamic programming table is storing Boolean values. If it is true, then basically we have to do the same. So I'm going to copy and paste it here. So we have to copy the value from the cell above. This is when we do not include the given item with index I or row index. And as far as else is concerned, here we do include the item I in the subset. So we have to use the formula we have been talking about in a theoretical section. The dynamic programming table with row index and column index is equal to the dynamic programming table with row index -1 and the column index minus the actual value of the integer. Okay, so after that, let's define the show result function. First of all, we have to check whether the last row and last column value is a true. If it is true, it means that there is a feasible solution for the subset sum problem. So we can print out that the problem is feasible and we get the last value of the table, whether it is true or false. And if we can check that if this entity is false, so if not and the entity, then of course we return, and otherwise we print out the items in the subset. This is what we have been talking about, that we have to consider the items right above each other, and if the values are not the same, then we are going to include the actual row as the item in the subset. And we keep going, and then we keep going until we hit 0 as the row index or the column index. Okay, so let's initialize the column index to be the self.m, so it is going to be the last column. We have the row index pointing to the last row in the dynamic programming table, and we can say that while the column index is greater than 0 or the row index is greater than 0, what do we have to check? We have to check the items right above each other, so row index, column index, and the item with row index -1, so the item above with the same column index. And if they are the same, of course, we just have to decrement the row index. It means that the given item is not part of the subset. And else, we know that the two items are not matching, so we print out, we take the item and we print out the num, so the integer with row index -1. And of course, we have to decrement the column index by the actual value. So this is what we have been talking about, that if the two values are not the same, then we are standing at column index 6. We include the item 1, so 6 minus 1 will be 5. So we decrement the column index by the actual integer, and we decrement the row index by 1. So this is why we decrement the column index by the actual integer, and we decrement the row index by 1. Okay, so let's check whether if the name is equals to the main, so we get the main function. The sum is equals to 9, and we have the integers, for example, n is a list data structure, 1, 2, 5, and 3. I guess the order is not matching, so the original order was 5, 2, 1, and 3. But anyways, of course, the order of the items doesn't matter, so we have the problem as a subset sum problem, and we have to define the numbers and the sum. Okay, and then we have to call the solve function, and then we have to call the show result function. Okay, so if we save and run it, of course we should get true. Okay, there's an error, self s row index -1 and column index list index out of range. Because here, whenever we instantiated this two-dimensional list, of course we have to use something like this. So this is going to be a single row basically with as many columns as m+1, and we are going to have as many out of these rows as the number of items in the integer list. So I guess that if we save and rerun the application, then it is going to work just fine. If we are looking for a subset that sums up to 9, of course 3 plus 5 plus 1 is equals to 9, so there is a feasible solution. If we are after, for example, 11, of course again we have to sum up all the values, so it is going to be feasible. What if we are looking for example, 20? Of course, there is no feasible solution, so we return false. So it is working fine. This is how we can implement the subset sum problem. And by the way, maybe it is not the best idea to use row index and column index, because as we have discussed in the theoretical section, we used I for row index and J for column index. So I am going to use J and I accordingly. I and J, I and J. Okay, so I guess that it is more straightforward at what's happening under the hood, because we have been using the variables I and J in the theoretical section. So if I rerun the application, then it is going to work just fine. If m is equals to 11, then we have 3, 5, 2, and 1. So this is how we can implement the subset sum problem with dynamic programming. Thanks for watching.